basis of the lab is this conduction in a square slab using Jacobi and Gauss-Seidel methods. And the idea is you fill out that sheet there. So you have a copy of it there, get a pen, fill it out. So what we're modeling is, so this square slab made of some material, we have the conductivity and so on. And so it's at 60 degrees along this face and 20 degrees along the other. So you're going to get heat transfer from the top out to the sides and the bottom. And what we're going to try and solve for is the temperature distribution there. And if I see the diagram beside that, figure 2 there, and you see that I've numbered it off. So like we have node 1, 2, right beside that is 2, 4, and 3 there, 3 and 4. So 3 is joined on to 2 and so on. Much as possible, I've tried to have consecutive numbers together, 5 and 6. And it's also symmetrical around this plane in the middle, so I've numbered these off 1, 4, and 5. But I'm not going to create separate solutions for them, but they're equal to 1, 4, and 5, so it's as if they're like that. The finite difference equation for pure conduction shows that the temperature at each node is the average of all nodes around it. So for example, node 1, let's go to 1 here. So that's joined to T2 plus T4. This one here is at 60 and this is at 20. So T2 plus T4 plus 60 plus 20 minus 4T1 will be equal to 0, meaning 4T1 is equal to the sum of all these. If we rearrange that a little, bring all the known quantities over on the right, so 60 plus 20 is 80, and multiply it by minus 1 as well. So you get 4T1 minus 80, so bring the 80 over, it comes plus, and you have minus T2 minus T4. So that's where we get the equation for node 1. And if you see it there, node 1, 4T1 minus T2 minus T4 is equal to 80. So if we go into, try that for node 2 here, I don't know if you can see it up on the board, but we do the same equation for node 2, we would get, so node 2 is connected to T1, so T1, also connected to T3, so T1 plus T3. It's bordering on, the one above it is at 60, it also has, to the right of it here, it has T1 again, so we'll do plus T1 again. Plus 60, that's the 4 neighboring ones, minus 4T2, and that's all equal to 0. And if we multiply that by minus 1 and rearrange it, bring the 60 over the other side, we'll get 4T2 minus 2T1, there's 2 T1s in there, minus, there's a minus T3 there, that's going to be equal to 60. So you see there, that's the equation for node 2. So take all the neighboring ones, add them up, minus 4T2, and then that gives you the equation. Arrange it so you have the variables on the left-hand side, the temperatures, and the constants on the right. So hopefully you'll be able to repeat that for the other nodes now, nodes 3, 4, 5, and 6. Basically, go back to the diagram, see what it's connected to, add up the connections, and then you have the energy balance for it. So for node 3, we'd have it's connected to 2, 4, and 6, and 4 again. Node 3 is just pure conduction. So if I go, so connected to 2, 4 twice, and 6. So G2 plus 2 T4 plus T6 minus 4T3, and that's equal to 0 because there's no 60s or 20s there. So I rearrange that a little bit now. Get 4T3 minus 2T T4 minus T2 minus T6 is equal to 0. And node 4, and that's connected to 1 and 3, 1, 3, and 5, and a 20. So T1 plus T5 and T3. 3 plus T5 to keep them in order. And that's equal to 0. Oh, sorry, minus 4T2. 4T4. I have to give you 4T4. T1 minus T3 minus T5. That's equal to 20 when you multiply it by minus 1. And work it from there. Same method again. Node 5 is connected to 4 and 6 and 2 20s. That will give you 4T5 minus T4 minus T6 is equal to 2 times 20, which is 40. And number 6 is connected to 5 twice and 3 and 20. 2 T5s, T3, T20, and 20. So we get 4T6 minus 2T5 minus, what else is it connected to? Connected to T3 minus T3, and that's equal to, it's just connected to a 20 there, so that's equal to 20. And I think we're ready to do our coefficients now. So for node 6, coefficient of T6 is 4 in there, minus 2T, minus 2T5, minus T3, all the rest are 0. Now you fill them in as per above. You fill them out as per the first one, fill them out there. So if I open up, and can't really access that there, so open up Notepad. Go to a new file. So for the first one, that's coefficients are 4. 1, 0, minus 1, 0, and 0. 6 coefficients. And it's important you don't leave a space at the end of the lines. And bring up the equations for each one. So for node 2, that's 4. That's minus 2, 4, minus 3. All the rest are 0. For node 3, it's 0, minus 2, 4, minus, and so 0. Node 3, we just put in, so 0, minus 1 for T2, minus 4 for, or sorry, plus 4. Plus 4, that should be for T3. And minus 1. plus 4. And for T4, it's minus 2. And there's also one for T6. Sure to leave a space in here. T6 is going to be minus 1. Let's check it out. So 4 minus 2 T4. T3 minus 2 T4 minus 1 T2 minus 1 T6. Node 4. T1, that's minus 1. Nothing for T2. Minus 1 for T3. And 4 for T4. And minus 1 for T5, 0 for T6. And that's 1, 2, 3, 4, round of 5. 0, 0, 0 for the first 3. Minus 1 for T4. 4 for T5. And 6 is minus 1. That's 1, 2, 3, 4, 5. The last one is going to be 0, 0, 0. 0 for T4, minus 2 for T5. Sorry, there's 1 in T3 as well, minus 1. And coefficient is 4 for T6. My matrix coefficient of file, if I save that as matrix.txt, lowercase. Save that. Yeah.
If we zoom in on the second row here, see there's a mistake here. It should be minus 1, as in minus 1 times T3, not 3. So that's a mistake. Change that to minus 1. And we file. Save that again as matrix.txt.
And now I have to save another one as orhs.txt. Which I put in the right-hand side of each of these equations again. Now, starting with the first one, that's the right-hand side is put them all in a row, 80, 60, 0, 20, 40, and the last one, T6, is 20. So put the right-hand side of each row in row. Okay, that's capital RHS.txt. Okay. So if you have those files saved, if you go to online-python.com, and we'll start that in a minute. That'll come up with some kind of, like it is on the screen there, it'll come up with some kind of sample thing. I'm going to just delete that. First thing we want to do is load those, open those files from your computer, matrix.txt and orhs.txt. So if you click on that folder there and click on matrix.txt first, open that. There it is. Open the folder again. Open file from disk and click orhs.txt. Open that. So we're going to write a program that will read them in as a matrix on the right-hand side, and oh, there they are. Matrix there, and the right-hand side there. So in main.py, that's where our Python code is going to go. So we'll start writing there in a minute once everyone is okay. Hope you're ready to start writing some Python now. First thing we're going to do is open that file, and put it in what's called an object called mat. So put in open. Name of the file is matrix.txt. Put that in quotes, and we need to specify that that's read only, because we're only reading from it. So we open our file there and put it in an object called mat, and from that we want to read the values of the coefficients into a variable, which we're going to call A, for the matrix A. So matrix is a two-dimensional list. Lists are denoted by square brackets. So that's A is equal to 2 square brackets. So that's a list in this direction and in the vertical direction as well, giving you, this case is going to give you a 6 by 6 matrix. So 2 brackets, we want to read them in as floating point numbers. So it's real numbers, essentially. Float n. And we need to put in a counter here for n in line dot split by t. So that reads in each individual component of each line. So it splits the line up into each line into individual components and reads each one in. So line dot split, close your brackets, open close brackets, they're round brackets. Then we have to do it for each line in that file, so for line in mat as well. So we read in each individual component on each line, and then we read each line after that. So 2 counters there through the line and then through each row. So this has 6 variables in it. So the order of our system is 6 by 6. We're gonna, let's see if I make that any bigger. Oh, there we go. Let's go down a bit. There we go. So we've created our matrix A. I'm going to create n is equal to the length of the round bracket, length of A, the first line of A, of any line of A. The length of A is 0. The first line of A is 0, so we set n equal to the length of the first line of A. So that's going to be equal to 6 in our case. So we're just setting n is equal to, well, the way counters work in Python, they go 0, 1, 2, 3, 4, 5, if there's 6 of them. So the first one is denoted as 0 for some reason. And we can now close that file. This is just good housekeeping. So mat.close. So now if we move on to opening the right-hand side and reading that in, so int for input, that is equal to open rhs.txt. It reads in the file rhs.txt, specify that it's read only. So int equals open rhs.txt, read only. That's going to be the right-hand side of our system. So we read that into a variable called B for Bravo. B equals float. I want to read them in as floating point numbers. So float n. I want to count through each line of that file or each component. So for in line dot int. So for each line int was only one dot, split that up into its components, 6 numbers in it, so it's going to count through all the members of the line and read them into the variable b. And then we're going to close that as well. Okay, I've just click the bottom at the bottom, the arrow at the bottom there, and run that. Found one error so far. That was I forgot to put the or, one of the ors for read only in commas, in inverted commas. So now it's running. hs.txt files as well. So that's our input read in. And we now have the variables A for the matrix, B for the right hand side. Need to create an initial guess and our solution X, which I'm just going to put equal to 0. I'm going to say X is equal to 0.0 for I in range N. So it's going to create 6 zeros. That's probably not the best guess because, well, we know temperature is going to be, all temperatures are going to be between 60 and 20. So probably better off putting in 20 there, maybe. Let's put in 20. That'll get us closer to the answer we actually want. I'm going to create another one then, identical, that's called Y. That stores the temporary solution in each iteration for X. And then at the end of that, we'll set X is equal to Y, so it doesn't overwrite the values of X. So this is Jacobi's method. It's about, you only need to change about 3 lines for to turn it into the Gauss-Seidel. That's the preliminaries done. We're now going to start the main iteration of this where we start solving. So start a for loop for k in range. And this is the number of iterations of the solution we want to do. I want to make sure it's going to give us a solution, so I'm going to put in 20 iterations. So I'm going to run the same algorithm 20 times. K in range 20. That's our iteration, and we need a colon at the end of that, so that it indents after that. So for k in range 20, colon, and it will indent. So everything that's indented 1 in there will be inside that loop. So for k in range 20, colon, brackets 20, colon. And if you put in the colon, it'll indent it automatically. I'll just bring up the algorithm here. So we want to put in this algorithm here. So xi k plus 1 is equal to b minus this sum. So it's the row of the matrix by the by x, excluding the diagonal. Divide that by the diagonal then. So that gives you your updated value of x. So we're going to put that algorithm in there. And we start by calculating that sum, which we call sum 0, and that's equal to 0.0. Start that, initialize that. Where that 2 came out of. equal to sum 0 is equal to 0.0. And we start an inner loop now where we go through every component of the matrix by column. So we're starting on row 1, and we go through it column by column, row by row, and column by column. So for I in range n, so we go through it row by row. First, colon. So after the 4, you put in a colon, it'll indent it again. So everything indented, that part is inside that loop. So for I in range n, oh sorry, little correction here. Take the sum and put it inside the for I, the second loop. So that for I loop takes you through it row by row, and next we have to go through it by column as well. So we go for in another loop for j in range n as well. So we have to go all through all 6 columns as well as the rows. So first loop takes you through row by row. This takes you through each column for each row. So for j in range n, and I'm going to put in a condition here. So if my column number j exclamation mark equals means is not equals to I. So as long as we're not on the diagonal, if j is not equal to I, j exclamation mark equals I, then it only carries out the calculation if j is not equal to I. Sorry, j, they have to be together. So if j is not equal to I, do the following calculation. Calculate the sum part for each from the algorithm. So we exclude the diagonal from the sum, and we, oh sorry, it's a semicolon I have in there, which is from C++, not Python. So if j is not equal to I, so if it's not, as long as it's not the diagonal, sum 0 is equal to sum we've calculated so far, sum 0 plus aij by xj. A square bracket I square bracket j. So every component of that row of the matrix, apart from the diagonal, multiplied by the solution we have so far, which is x. So that goes through that particular row I and multiplies it by our solution so far, x. So aij by xj. Add all them up. Now, and that goes through every row, calculates the sum, so multiplies the row by the solution x, excluding the diagonal. So this excludes the diagonal here. So I want to get out of that loop. So I delete back a few spaces. And I'm just going to see where I'm going here. And I'm also getting out of the if. So back out of this j loop and out of the if statement there. So I'm going to do this once per row. So it's inside this for I in range n loop. So it does this once per row where we calculate the solution y. So y square bracket I, that's equal to b I, the right hand side, minus sum 0, sum we've calculated so far. That all needs to be divided by the diagonal. So I'll throw brackets around a bit above the line, and divide that by the diagonal A, I. So where the row number equals column number AII, that's the diagonal. Now I'm going to take it outside. So that's the solution calculated for each row now when it goes through both of these loops. If I bring it back in line with for I in range n, now I want to overwrite. So it's calculated the full solution y now, and I want to set y now, or x equal to y, my solution for this iteration. So if I do a 1 to 6 loop for I in range n, do a loop of that, and I just set x I is equal to yi now. So y was only a place to store the solution temporarily. We now override x with that. So x was the guess we had going in. Override that with y now, which we've calculated. And the last thing we're going to do on the iteration is, for each iteration, is to print out the solution. Now, I want to print them out. It's going to, if I just print out the solution, print x equals, it will print them out to 12 decimal places. So I only want it to the nearest whole number. So I'm going to round it off to 0 decimal places. It's a bit more awkward to write out, but it's worth doing. So for each iteration we do, we first print out the iteration number, k. We're going to do 20 iterations. We're going to see how the solution develops with each subsequent calculation. Print k, and then the first thing we write out is the first component of x rounded off. So we do x round x 0, 0. Remember, the first component of every list is 0. The computer thing, we do round x 0, 0, and that's rounded off to 0 decimal places, the nearest whole number, comma 0. So round square bracket 0, square bracket 0, and then comma. Sorry, no, there's only one component in each. In x, there's only one index, so it's just round x 0, comma 0. And so that's an. Now, if we take the comma and that statement, round statement there, copy that, and just copy that inside the brackets there. We can change that to round 1, 0, and round x2, and so on up to x5, the fifth component. Right, x3. So we're just going to write out all the write them all out as a list. x3, x4. Was 0, and final one will be x5. So you do a print statement, and you write out k, x0, x1, x2, x3, x4, x5, all rounded off to 0 decimal places. And so you print out the solution as a whole number. And we're going to check our solution, and once that's the same for 2 iterations, that's the same to the nearest whole number, we know we've reached our desired level of accuracy. So next we're going to have to debug this because we've probably put in the occasional wrong bit. So wait, run this by clicking on the arrow down here. So most common types of errors of this are indent errors where they're not indented correctly. I'm getting one here for line 20, so I'll go to that. You can see here, line 20 here, it needs to go back 1. Okay, so let's fix that.
So here we see our solution along the bottom. This is for iteration k is equal to 19. We're seeing that t1 is equal to 37, t2 is equal to 41, t3 30, t4 27, t5 23, and t6 24. So maybe write them in, those temperatures in on the diagram on figure 1, so you get an idea of the temperature distribution. What I'm going to do is scroll through these solutions and see at which point it reaches the correct answer to the nearest whole number, which is how these are printed out. And so it's all the same here, so to reach the correct answer there. So 37, 41, so see it's changed here from 29 to 30 on iteration k is equal to 12, which is actually the 13th iteration, because remember the first one is 0. So we note down that it reaches this correct solution to the nearest whole number after 13 iterations here on k is equal to 12. It doesn't change after that. The next step is I'm going to show how to convert this Jacobi's method into a Gauss-Seidel method, which should give quicker convergence and require less storage. So if I do Control C, select that and Control C and add a new file here and click that in there. What I need to do with this then is get rid of the temporary variable y and make it so that it overwrites x, the value of x, with a new value of x as soon as it calculates it. That will give quicker convergence. So it's actually Gauss-Seidel is actually easier to use, easier to program. So I go through this here, and first instance of y is here. Just delete that for k in range. So I'll repeat for 20 iterations for I in range n. So instead of yi is equal to bi minus, I put in xi is equal to bi minus the sum. For I in range n, I can just get rid of these two as well. So now I don't need to overwrite x with y, which shortens it down a bit. And so now I'm going to try that running this. See, does it give me the same answer, and does it do it any better? So click run. So it ran there. 19, 37, 41, 30, 27, 23, 24. It's the same answer. Let's scroll up and see how 37, 41, 30, 27, 23, 24. After 9 or 10 iterations there. 30, 27, 23, 24. Now, looking for where it changes, 28, 29. So it's on k is equal to 6 here. We get that solution we got from Jacobi after 13 iterations. But Gauss-Seidel does it after 7 iterations. You can see it's quicker to converge. It uses less storage because you've got rid of the variable y as well. So it uses half as much storage and is generally more efficient as an iterative solver. So that's the 2D conduction lab, and we shall see you later.